Okay, we'll finish up this presentation with a quick look at some other methods, large-scale PV and medium voltage. Other methods. I do want to point out that the methodology we've presented is peer-reviewed, it follows industry best practices, and it's a valid way to size conductors. There's also lots of other ways to do it. Lots of other ways. Some are just variations on the approach we've taken. Other ones are much more advanced engineering projects that are undertaken. Some of these are beyond the scope of the course, right? So there are different ways to do this, and you want to keep that in mind. In fact, the NEC expressly allows other methods, such as in 31014B. Here's a look at the calculation that can be done under engineering supervision. We're not going there. We're not going there. This is beyond the scope of the class, but do keep in mind that, especially on larger systems, engineering dollars can pay off in terms of cost savings. We want to engineer the system to be safe and effective, and there's opportunities to save there on things like breaker size, wire size, conduit size, things that can really add up as we have larger and larger systems. One method I want to talk about briefly is 690.8 A1A2. These would be for source circuits where we have a system with a generating capacity of greater than or equal to 100 kilowatts. Generating capacity, defined in Article 100, it is the rated output power of an inverter or inverters at 40 degrees Celsius. So we're really talking the AC side of the system here, not the DC. Don't care how big the array is. How big is your AC system? If you're greater than or equal to 100 kilowatts, then we have an allowance to use an alternate method to calculate maximum circuit current. We know that's the basis for the OCPD size and the wire size. So if we can fine tune our calculations on maximum circuit current, it may allow us to use smaller breakers, smaller wires, smaller conduit. Again, want to maintain system safety, but this is an opportunity to reduce costs a little bit. Has to be performed by a licensed professional engineer, and they have to use an industry standard method. They've got to document it, and this calculation has to be part of the system design that is stamped by the engineer, submitted for a permit to the authority having jurisdiction, part of the design of the system. And essentially what we're doing here is using a software modeling package to determine what the highest 3-hour average current is. And the reason this is an advantage is because we can calculate this or model this based on the actual attributes of the system. You know, what's the tilt angle? What's the orientation? What's maybe the shading that we're encountering? Those are kind of things that the general rules that we've talked about thus far, those nuances are not taken into account. We're just looking at what is the short circuit current of a module. Well, here we're saying, well, what is the module actually going to do based on the way it is installed? And that potentially leads to a lower maximum circuit current value. And as I said, lower, smaller wire, smaller breaker, smaller conduit. So cost savings here, still designing it safely. And in fact, the code says that this calculated value that you get by modeling the output and seeing what that highest 3-hour average current is cannot be less than 70% of that maximum circuit current, ISC times 1.25. So if you do the math, ISC times 1.25 times 0.7, you'll see that the lowest we could go would be ISC times 0.875. That's 1.25 times 0.7. So that's kind of less, right? We're saying that normally ISC times 1.25 is our maximum circuit current. Depending on how we model it, we could come up with a maximum current somewhere between that and ISC times 0.875. That's as low as we can go. Even if the model says, hey, it's less, you can't go below that, 70% of the maximum current. So this, again, is a potential for some significant savings depending on how the system is actually going to operate. Large-scale PV has some of its own allowances. These are systems that are over 5 megawatts generating capacity, so 5 million watts of inverters. And this, again, are allowances for professional electrical engineers. They've got to be part of the stamped plan set, documentation, details have to be provided. But here we can do things like, again, circuit current, conductor ampacity, maximum system voltage calculations. Provided these are being done following industry standard methods that are documented by a licensed PE, these can be valid and submitted as part of a permit package for a plan set. Finally, medium voltage conductors and cable. Medium voltage is defined in the NEC as 2001 up to 35,000 volts. These aren't always the same definitions of medium voltage when utilities talk about them, but these are the conductor ratings you would see. Article 311 covers medium voltage conductors and cable, first introduced in the National Electrical Code in the 2020 cycle. And, these are used on bigger systems all the time, either for interconnection to the grid through a substation or other medium voltage equipment, or in some cases on large systems, we also use them as AC aggregation or collection systems, where we have multiple large inverters spread out across a site. The inverters are putting out through a transformer something between 2,000 and 35,000 volts, and we're running medium voltage around to those transformers to pick up all of that current. Something that we do see often done. Well beyond the scope of this class. Just keep in mind, the takeaway here is if you are getting roped into sizing medium voltage conductors, you didn't learn enough about it to do it here, and there are differences. So really just want to make sure that people are aware of that. Okay, that wraps up our conductor and overcurrent protection sizing lesson. Hope you enjoyed it. I'll catch up with you in another lesson somewhere soon. Bye.